So dear participants, let's get back with our discussion on timers in PLC. In our last lecture, we have got a generic concept of timers. We have seen that it is not the PLCs that only contain timers actually. There are independent timing devices available extensively across the industry, where actually there is no PLC required, but some timing application has to be taken care of. There such type of independent modules are used. However, we have also seen that PLCs, they also contain timers invariably. And nowadays, when every automation equipment is installed with number of PLCs, any automatic process is installed with number of PLCs, then it is always better to use the timer which is already available with the PLC in order to minimize the hardware and its ancillary wiring. Now you see, so for the timers in PLCs are concerned, we have seen that there are three basic type of timers that are available with PLCs. One is the on delay timer, other one is the off delay timer, and the third one is the pulse timer. So this is where we had stopped in our last lecture, and let us start from this point onwards. You can see here, these are the basic IEC symbols that are used for timers. You should remember the name IEC, that is International Electrotechnical Commission. They prepare and decide the standards for these automation process equipment, electrical equipment and all such things. So the particular symbol that they give, that are used throughout the world as a standard, and the three standard symbols of on delay timer, off delay timer and pulse timer is there in front of you. You see this T, you can see this, I will just take this, sorry, okay, you can see this T stands for timer in every case. When it is on, that indicates an on delay timer, this T off indicates an off delay timer, and this TP indicates a pulse timer. You see here what are the other things present in this block. So this block becomes the timing block, where there are four different notations. One is in, next is Q, then there is one PT, then there is one ET. Now this in signal, in terminal, that accepts only Boolean input. This terminal is meant for providing necessary signal towards triggering the timer. Then there is this Boolean output which is available at Q. So whatever the timing relay condition, that is available at this Q, either it is 1 or it is 0. Therefore they are called the Boolean signals. Now in this PT, we actually give the programmed time value, the particular timing that we want to program, or the preset time duration that we actually feed here in this PT. And finally we have this ET, which shows the elapsed time. Means that if we want our timer to give a delay of 100 seconds, so that 100 seconds we need to put in this PT. And finally this elapsed time will help you to see how much time has been passed since the first operation of the timer during that particular cycle. Okay, so you can find this elapsed time to increase like this: 0, 1, 2, 3, 4 till 100. Once it reaches 100, that means the timing operation is done. So this is the IEC 61131 standard that gives this nomenclature. Now let us see what are the basic timing operations that are there in the PLC. So here you can find the timing diagram. You can find here, this is the on delay timer. This is the on delay timer in which we are giving this input trigger. The moment we trigger the timer, elapsed time starts. Elapsed time means the time which is passed after the input trigger has been provided or has been applied. Now you could see here that if suppose I have given an PT, that means preset time of 5 seconds, then once this 5 seconds is over, then you have got the timer output. This is simple. Now you can see as the input trigger goes from 0 to 1, the elapsed time starts to increase. And when it reaches the time specified by the input PT, you can see here, you can see this line, and this is the specified time PT. That means the time you have programmed, for which you have programmed the timer and or the preset time. Okay, so once it is done, the output changes its state from 0 to 1. This is the case of on delay timer. Now in case of an off delay timer, what you can see that once the input trigger is absent, or in case of PLC we can say that the rung condition, if we talk of the ladder diagram, if the rung condition goes false, because generation of an input may so reflect that the rung condition goes true, and in this case the rung condition goes false, that means you have no signal. At this point, whenever there is no signal at the input, earlier there was signal and at certain point of time there is no signal. The moment when the signal goes from on to off, the time starts increasing, and the time will increase for the preset duration. And you can find here that the timer output was available along with the input. Once the input is no more, then also the timer output is remaining on. However, when you reach the preset time duration that you had already fed to the timer, your timer output goes to 0. And finally, you have got this pulse timer. For the pulse timer, you need a continuous input, and for your preset duration of time, you will get the pulse. Now you can see that this timer gives an output 1 for a fixed period of time, starting when the input goes from 0 to 1 and switching back to 0 when the set time PT has elapsed. You can see it is going from 0 to 1 and it goes back to 0 when the switch is PT, that is the preset time, is completed. Completed means elapsed. That's why the name elapsed time, khatam hone wala waqt. Now you can see the time duration. This you please remember, this is very important terminologies that you need to keep in your mind. You see, the time duration for which a timer has been set is termed the preset, for which you are actually programming the timer. It is termed as preset and is set in multiples of the time base used. This time base is very important concept when we are dealing with timers. Now you see the time bases that are typically available with PLCs are 10 millisecond, 100 millisecond, 1 second, 10 second and 100 second. Now you see the basic point is why we use time base. We use time base in order to have a very wide range of preset time duration. Suppose your time base for a particular timer is 10 millisecond. You have 10 millisecond. Now you need a 1 second. You need a 1 second delay to be generated, or 1 second preset you require. Now for that, how much preset you will have to give? You will have to give 100, because 100 into 10 millisecond is equal to 1 second delay. However, with the same PLC, if you use the time base of 100 millisecond, under such circumstances, you need to give the preset value of 10. Right, you need to give the preset value of 10. So once you give the preset value of 10, then your time duration will be 1 second. So that is the fact. Either you can consider it as the preset value, or you can consider the time duration as the preset value. If the time duration is known to you and you consider it to be the preset value, then you have to multiply this time base with some constant. In most of the cases, this constant is denoted as K. I will show you the example. Okay, so the official process is to consider the preset as the time duration. So if I say that a delay of 1 second is required, then 1 second is the preset. Your time base is 100 millisecond. So now you need to decide that what constant factor has to be multiplied with the time base in order to get the preset. The third and final example, suppose you have to generate a delay of 100 seconds, and if you have a time base of 1 second, then what is the preset? The preset is 100 seconds. Time base is 1 second. So what is the constant factor by which you need to multiply the time base? That constant factor is 100. So once you multiply the time base with 100, where your time base is 1 second, then your preset value becomes 100 second, like that. So that's why you can see here a preset value of 5 with a time base of 100 millisecond is a time of 500 millisecond, likewise. Okay, now you see. So in PLC ladder terminology, this is another important concept that you need to be very careful about, that there are different approaches of timer treatment in PLC ladder terminology. That means whenever we are using PLC ladder terminology, then for different PLCs or different manufacturers, they have different approach to treat with timers or to represent the timers in the ladder diagram. You can see here in this particular case, the timer has been treated as an output for a rung. You can see this is the timer coil. That means it has been treated as an output for a rung. This is one of the rungs and this is the output, while control being exercised over pair of contacts elsewhere. However, when this is the output coil, the NO contacts of the coil, which are actually important in order to have some operation, those contacts are placed at other rung in the same ladder diagram. Or in some cases, the timer is treated as a delay block. You can find the timer as a delay block that is inserted in the rung. And when it is inserted in the rung, it actually delays a signal in that rung from reaching the output. Very simply, if you have got a delay of 5 seconds given to the timer, then you see when you put this contact on, or the rung condition is true, it is more technically correct statement. The rung condition is true. That means this is connected. So once this is connected, if there was no timer, then the output should have been changing the state. However, the presence of this timer will result a delayed actuation at the output. So how much delay it will be there at the output? The delay will be of the same period for which you have programmed the timer. This is the basic concept of using block type timer in the ladder diagram. Now let us go for some of the examples. In this particular case, I will be showing you notations of different manufacturers, but it is not possible every time to show you notation of different manufacturers. I will mostly rely with the Allen Bradley notation, but time and again I am advising you that you please take care to go for YouTube or technical documentation of PLCs from different manufacturers so that you are well versed with the notations. Okay, now remember one important concept, that all PLCs generally have on delay timers. So on delay timers are common factor in every PLC. Even if that PLC is not having any other type of timer, on delay timer must be there, because this is the most fundamental function in timing terminologies. So therefore, even the smallest possible PLC that is having an on delay timer embedded into it. Now let us see the Mitsubishi notation. Here you can see the ladder diagram for on delay timer. This X400 is actually an input to rung 1, and you can see this timer 450. The T is the timer, the number of the timer is 450. So when this input contact is changing the state from off to on, now you can see this is a normally open contact. When we close it or when the rung condition is true, then the timer is activated. Once the time delay is over, you can find the contact of the timer. The contact of the timer coil is present on the second rung. So whenever this timing delay is over, then this contact will become closed. Earlier this was open, now this will become closed, and you will get the output here. So this is the basic on delay timing operation when we are talking in the terms of Mitsubishi notation. You can see that timer coil is present in one of the rungs, and the contacts which are actually important in implementing the timing operation, that is present in the second rung. Now you can see this. If there was no timer, then this input would have directly connected to the output. But here the coil and its contacts, they have made the timing operation possible in case of Mitsubishi PLCs. Now let us talk of Siemens notation. In Siemens notation, we do not take the timing coil in one of the rungs and timing contacts in another rung. Here the timer acts as a delayed item in the rung rather than a relay. Earlier you can find here that this was acting simply as a relay. This is the coil and this is the contact. But here in case of Siemens, it is not acting as a relay. It is acting as a delay block. Now you see, when the signal at the timer's start input, this is the S, that means the start input, changes from 0 to 1, that is the rung condition is true, the timer starts and runs for the programmed duration, giving its output to the output coil. The time value, you can see this is the TV, time value output, this is an output pin. Very importantly, this is an output pin, TV. Can be used to know the amount of time remaining at any instant. समझ लीजिए आपने 100 सेकंड के लिए इसको टाइमिंग दिया हुआ है, तो किसी एक वक्त पे कितना सेकंड बाकी है ये अगर आपको जानने की जरूरत पड़े, then you need to use this particular terminal where the remaining time is always displayed. This R is the reset input. A signal input of 1 at the reset input resets the timer whether it is running or not. Even it is in a condition of running, then also it is going to be reset if the reset terminal is high. Now you see how we are actually entering the preset time into the timer. This varies from PLC model to model, even in Siemens, right? Normally there is a constant K command which will have to feed during the programming of the PLC. Okay, so once that K command is there, after that whatever this value we put, that value will be multiplied with the time base. To generate the delay. Okay, so this is basic concept of this on delay timer in Siemens notation. This is the binary and BCD output of the timer, because these values, whatever the timing values are there, they are reflected in BI and BCD formats. They are kept in registers for certain operation. And now this is on delay timers in Allen Bradley RS Logix notation. Okay, here you can find that this is the on delay timer. Again here it is a block. It is very detailed in case of this Allen Bradley. Now you can find that there are two coils, or rather two outputs that we are getting out of the this time delay block or the timer block. One is EN. EN means enable bit, and DN. DN means done bit. Now you can see that things are very clear in Allen-Bradley notations. First, the timer with the type is written on delay. Then the number of the timer is given T4.1. Then the time base is given 1 second. Then the preset value you have to put here 50. You are putting the preset value. So when you are putting preset value 50, the time base is 1, then the total delay that is going to be generated by this timer is 50 seconds. If the time base is 10 seconds, then your preset is 50, so the time delay that will be generated is 500 seconds. Now you can see here that all these coils, they are having their respective contacts in the following rungs where the actually timer is present. Here is the timer block and here are the different rungs, following rungs where we have put the contact of the enable coil and the DN coil. Now you can see here I have clearly written the Allen-Bradley have 3 boolean bits for ladder logic control. You have got 3 boolean bits here. One is the timer enable bit EN. This goes on when the timer accumulator is incrementing. So what is the purpose of EN? The purpose of EN is, suppose your time starts from 0. Your time starts from 0 and it has to go up to 500. Then there is an accumulator in the timer. You can actually see it. The values of the accumulator, continuously changing values, you can see them when the programming is taking place or the program execution is taking place. At that condition, the timing value in the accumulator that increases from 0 to 500. Now, the moment from which the accumulator starts counting till the accumulator stops counting, your enable bit remains high. Then there comes the done bit, DN, done bit. Once the timer job is over, that means you have achieved the preset delay, then this done bit goes high. And there is a timer timing bit which is denoted by TT. It is kept on when the accumulator is incrementing and remains on until the accumulator reaches the preset value. So this is very clear. You need to be very alert about these 3 terminologies, and with the help of these 3 bits you can definitely control your operation. I will show you the timing diagram now. You can see here, this is the input signal. This is the input signal, and as we have told, the preset value is 50, the time base is 1. So delay that is going to be generated is 50 seconds. Now you can see that accumulator value will go from 0 and it will go up to 50. For this entire 50 second, this TT will remain on. Once this 50 second is over, the TT is going to be off. You can see over there what we had discussed. Keeps on when the accumulator is incrementing and remains on until the accumulator reaches the preset value. Tick. Next, we can see the enable bit. For the entire period for which the input is present, you have the enable bit high. The done bit will remain high, or the done bit will become high when the TT, that is the timing operation, is over but your input is present. The done bit will become 0 when the input is absent. And finally, if you take the NC contact or the reverse contact of the down bit, then you will have completely opposite operation than the down bit. That is the reverse operation of the down bit. So you can just verify your concepts. The timer enable bit, it goes on when the timer accumulator is incrementing. It will keep on till the final time for which the entire input duration is there. Your enable bit will be there, because whenever the signal is there, timer is enabled. Very simple. Whenever the signal is there, the timer is enabled. So till the signal is present, your enable bit will remain high. Timing bit will remain high when the accumulator is incrementing. When the accumulator stops incrementing, it will come low. The done bit, it will go high after the set time delay is over, and it will remain on, or it will remain high till the input is present at the timer input. Now you can see the Allen-Bradley timer symbol shows the type of timer concerned, the timer address, and the time base. That indicates increments by which the timer moves to the preset value. The time base have several values such as 0.001 second, 0.01 second, 0.1 second, or 1 second. Now there is a preset value. It is given as PRE. It is the number of time increments that the timer must accumulate to reach the required time delay. टाइम डिले तक पहुंचने के लिए जो टाइम जमा करना पड़ेगा, कहां पे जमा करेगा? वो एक्यूमुलेटर में जमा करेगा. और प्रीसेट वैल्यू क्या होता है? नंबर ऑफ टाइम इंक्रीमेंट्स दैट द टाइमर मस्ट एक्यूमुलेट. उतना टाइमर को उतना टाइम जमा करना पड़ेगा. कितना टाइम? प्रीसेट वैल्यू में दिया हुआ टाइम. ओके, द एक्यूमुलेटर इंडिकेट्स द नंबर ऑफ इंक्रीमेंट्स दैट द टाइमर हैज एक्यूमुलेटेड व्हाइल द टाइमर इज एक्टिव. जो टाइम धीरे धीरे बढ़ रहा है वो टाइम आपको कहां पे जमा होता है? एक्यूमुलेटर में जमा होता है. डेफिनेटली एक्यूमुलेटर इज अ रजिस्टर, otherwise how can that time increment? That will be temporarily stored somewhere. So for that, accumulator is the register in which this incrementing time value is continuously getting updated. Once the timer is reset, the contents of the accumulator is reset to 0, no doubt. Now you can see this is another timer symbol. This is another timer symbol. Again, this is of Allen-Bradley. But this particular timer symbol is there for connected component workbench environment of micro 800 series of PLCs. Here you can see that there is an in terminal, which is a Boolean input accepting terminal. There is a Q terminal, which is a Boolean output terminal. Then there is PT, in which you are actually giving the preset time value. Here you can see T, then there is a hash symbol, and finally there is 10S. Hash means you are directly giving the time duration, and ET shows the time elapsed. Whenever this run condition is true, then the ET starts increasing from 0 to final value. Once the final value is reached, your output changes the state. Very simple. Now we will go for sequencing operations using on delay timer, which is more related to the application part of the on delay timer. We will discuss this, and before starting discussion on such application part, we will, in our next lecture, we will see some basic programming with timers. So thank you for now.